Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Pierre-Gilles' De Genus Soft Matter, published in 1990, represents a watershed moment in the consolidation and popularization of an interdisciplinary field. Rather than presenting novel research, the book synthesizes existing knowledge from polymer physics, liquid crystals, colloids, and granular materials, offering a unified perspective based on scaling concepts and phenomenological modeling. This essay provides a critical evaluation of De Genus' core arguments and specific claims, dissecting the book's structure and assessing the validity of its approach in each section. The focus remains squarely on the internal consistency and persuasiveness of De Genus' presentation, considering its impact and subsequent developments only as they illuminate the book's initial assertions. Section 1, Introduction and Overview of Soft Matter. De Genus begins by defining soft matter as systems exhibiting a significant response to thermal fluctuations and external forces, a definition broad enough to encompass the diverse materials under consideration. He emphasizes the importance of understanding interactions at the mesoscopic scale, larger than atomic dimensions yet smaller than macroscopic domains. The critical claim here is the possibility of a unified theoretical framework, based on analogies and scaling laws, applicable across seemingly disparate systems. This framework, he suggests, can predict macroscopic properties from microscopic interactions. A potential point of contention arises immediately the breadth of application claimed. Can a single theoretical lens truly capture the nuances of polymer melts, liquid crystals, and granular media without sacrificing precision? De Genus acknowledges the limitations of such a generalized approach, but insists upon its heuristic value. He argues that identifying universal behaviors, even at the cost of some specific details, provides a valuable roadmap for further investigation. Section 2, Polymers, Chains in Solution and Melts. This section delves into the statistical mechanics of polymer chains, both in dilute solution and in concentrated melts. De Genus reiterates Flory's mean field theory, introducing the concept of the excluded volume effect and its influence on chain conformation. The central claim is that the size of a polymer chain in solution scales with the number of monomers, raised to a power that depends on the solvent quality. Specifically, he states that the radius of gyration, represented as r sub g, is proportional to n raised to the power nu, where n is the number of monomers and nu is the Flory exponent, approximately equal to 3/5 Pierre-Gilles solvent. The book presents a scaling argument to justify this exponent, based on balancing the excluded volume energy with the entropy of the chain. This argument, while elegant, relies on several approximations. The assumption of uniform monomer density will in the chain neglect local fluctuations, and the treatment of the excluded volume interaction as a simple pairwise repulsion is a simplification. Subsequent work has refined these approximations, leading to more accurate predictions, though the fundamental scaling relationship remains valid. De Genus then transitions to polymer melts, arguing that chains in a melt behave effectively as ideal chains, due to screening of the excluded volume interaction. This claim, known as Flory's ideality hypothesis, is supported by experimental evidence from neutron scattering. He discusses the concept of entanglement, where topological constraints imposed by neighboring chains restrict the motion of a given chain. He states that the mean squared displacement of a monomer, denoted as g sub 1 of t, exhibits two distinct regimes: a short-time regime where g sub 1 of t is proportional to the square root of time, and a long-time regime where g sub 1 of t is proportional to time to the power of 1/4. This difference reflects the transition from Rao's dynamics at short times to rotation dynamics at long times. Section 3, Rotation and Tube Models. De Genus introduces the rotation model to describe the dynamics of entangled polymer chains. This model postulates that a chain moves primarily along its own contour, confined within a virtual tube formed by surrounding chains. The key claim is that the diffusion coefficient of a chain, represented as d, scales inversely with the chain length, n squared. This result arises from the fact that the chain must snake its way out of the tube, a process that takes a time proportional to n cubed. This reptation model, while providing a valuable conceptual framework, has limitations. It neglects chain fluctuations perpendicular to the tube and assumes a uniform tube diameter. Refinements to the model have accounted for these factors, leading to more accurate predictions of the viscoelastic properties of polymer melts. Directives discusses the concept of the Plateau modulus, G sub n, which characterizes the elastic response of the melt at intermediate times. He claims that G sub n is inversely proportional to the entanglement molecular weight, m sub e, the average molecular weight between entanglement points. This claim reflects the fact that the stress is supported by the entanglements, and a higher entanglement density leads to a stiffer material. The reptation model predicts specific forms for the viscoelastic relaxation modulus, G of t, which can be compared with experimental data. Directives shows that the model captures the qualitative features of the relaxation process, but discrepancies exist, particularly at short and long times. The model's success lies not in its perfect accuracy, but in its ability to provide a physical picture of chain dynamics and to predict scaling relationships that are qualitatively correct. Section 4. Liquid crystals, order and defects. This section shifts focus to liquid crystals, materials that exhibit orientational order intermediate between that of a crystal and an isotropic liquid. Directives classifies liquid crystals based on their symmetry, distinguishing between nematic, cholesteric, and smectic phases. He claims that the free energy of a liquid crystal can be expanded in terms of order parameters, which quantify the degree of orientational order. For example, the nematic order parameter, S, represents the average alignment of the molecules along a preferred direction. The director, he states that the transition from the isotropic phase to the nematic phase is typically a weakly first-order transition, driven by the competition between entropy and orientational interactions. He invokes the Landau-Directives theory, based on expanding the free energy and powers of the order parameter, to describe this transition. This theory predicts that the order parameter jumps discontinuously at the transition temperature. Directives emphasizes the role of defects in liquid crystals, topological singularities in the director field. He claims that these defects are unavoidable due to the constraints imposed by the orientational order. He distinguishes between different types of defects, such as disclinations and point defects, and discusses their energetic cost. The presence of defects affects the macroscopic properties of liquid crystals, such as their optical and mechanical properties. Directives argues that understanding the structure and dynamics of defects is crucial for controlling the behavior of liquid crystal displays and other devices, while acknowledging that a complete theoretical description of defects remains a challenging problem. Section 5. Dynamics of liquid crystals, director fluctuations and flow alignment. Directives extends the discussion to the dynamics of liquid crystals, focusing on the fluctuations of the director field and the effects of flow. He claims that the director fluctuations are described by a diffusive equation, with a diffusion coefficient that depends on the elastic constants and viscosity coefficients of the liquid crystal. In particular, he states that the relaxation time of a fluctuation with wave vector q is inversely proportional to q squared. This result reflects the fact that smaller wavelength fluctuations decay more rapidly. He discusses the phenomenon of flow alignment, where the director aligns with the flow direction under shear. He suggests that the alignment angle depends on the ratio of the meso-rich viscosities, which characterize the resistance of the liquid crystal to flow when the director is aligned along different directions relative to the flow. The analysis assumes a simple Newtonian fluid description, which may not be adequate for all liquid crystal systems. Directives acknowledges that the flow behavior can be more complex, particularly at high shear rates, where turbulence and other nonlinear effects can occur. He proposes that the coupling between the director field and the flow field leads to interesting hydrodynamic instabilities and pattern formation. Specifically, he mentions the possibility of oscillatory instabilities and the formation of periodic structures in the director field. These instabilities affect the performance of liquid crystal devices and are an active area of research. Section 6 Colloids, Interactions and Phase Behavior. This section addresses colloids, dispersions of particles in a liquid medium. Directives claims that the stability of a colloidal dispersion is determined by the balance between attractive and repulsive interactions between the particles. He outlines the Directives-Landau-Verwey overbeek DLVO theory, which considers the interplay between van der Waals attraction and electrostatic repulsion. He states that the van der Waals attraction is a long-range force proportional to the inverse sixth power of the distance between the particles, while the electrostatic repulsion is a short-range force decaying exponentially with distance. The DLVO theory predicts the existence of a potential energy barrier that prevents the particles from aggregating. However, the theory relies on several assumptions, such as the additivity of van der Waals forces and the validity of the Poisson-Boltzmann equation for the electrostatic potential. Directives also examines the effects of steric stabilization, where the particles are coated with polymers and prevent them from approaching each other too closely. He claims that the steric repulsion arises from the compression of the polymer layers when the particles are brought together. He discusses the phase behavior of colloidal dispersions, including the formation of ordered structures such as crystals and glasses. He suggests that the phase diagram depends on the particle concentration, the interaction potential, and the temperature. He notes that the formation of colloidal crystals is driven by entropic considerations, as the particles pack together to maximize their free volume. Section 7 Gels, Networks and Swelling. Directives considers gels, materials that are solid-like yet contain a significant amount of liquid. He claims that a gel consists of a network of cross-linked polymers, which provides structural integrity, and a fluid phase, which fills the space between the polymer strands. He discusses the swelling behavior of gels, where the gel absorbs liquid and expands in volume. He states that the swelling is driven by the osmotic pressure difference between the gel and the surrounding liquid. The osmotic pressure arises from the difference in polymer concentration and the presence of ions in the gel. He provides a scaling argument for the swelling ratio, which is the ratio of the volume of the swollen gel to the volume of the dry gel. He claims that the swelling ratio scales with the cross-link density. Raised to a negative power, he acknowledges that this scaling relationship is only approximate, as it neglects the effects of chain connectivity and topological constraints. Directives also examines the mechanical properties of gels, such as their elastic modulus and their response to applied stress. He suggests that the elastic modulus is proportional to the cross-link density. He discusses the phenomenon of gel collapse, where the gel undergoes a discontinuous volume change in response to a change in temperature or solvent quality. This collapse is driven by the competition between the elastic energy of the network and the mixing energy of the polymer and solvent. Section 8 Adhesion and wetting interfaces and capillarity. This section examines the phenomena of adhesion and wetting, which involve the interaction of liquids with solid surfaces. Directives claims that adhesion is determined by the interfacial energy between the two materials in contact. He introduces the Young equation, which relates the contact angle of a liquid droplet on a solid surface to the surface tensions of the solid-liquid, solid-vapor, and liquid-vapor interfaces. He states that the contact angle is a measure of the wettability of the surface. A small contact angle indicates good wetting, while a large contact angle indicates poor wetting. He also discusses the effects of surface roughness and chemical heterogeneity on wetting. He suggests that roughness can enhance or reduce wetting, depending on the length scale of the roughness. Chemical heterogeneity can lead to pinning of the contact line, which prevents the droplet from spreading smoothly. Directives discusses the dynamics of wetting, focusing on the spreading of a liquid droplet on a solid surface. He claims that the spreading rate is determined by the balance between capillary forces and viscous forces. He introduces the Tanner's law, which states that the spreading velocity is proportional to the capillary number, raised to a power. He acknowledges that this law is only valid for thin liquid films and the spreading dynamics can be more complex for thicker films. Section 9. Granular matter packing and flow. Dijens moves to granular matter, assemblies of macroscopic particles such as sand or gravel. He claims that granular matter exhibits unique properties, distinct from those of solids, liquids, and gases. He emphasizes the absence of thermal fluctuations, which play a dominant role in the behavior of other soft matter systems. He states that the properties of granular matter are primarily determined by the mechanical interactions between the particles, such as friction and inelastic collisions. He discusses the packing of granular particles. Focusing on the concept of random close packing, he suggests that the packing fraction, which is the ratio of the volume occupied by the particles to the total volume, approaches a maximum value of approximately 0.64 for randomly packed spheres. This value is less than the packing fraction for ordered structures, such as face-centered cubic or hexagonal close-packed lattices. Dijens examines the flow of granular matter, focusing on the phenomenon of avalanches. He claims that avalanches occur when the shear stress exceeds a critical value, leading to a sudden failure of the material. He introduces the concept of the yield stress, which is the minimum stress required to initiate flow. He also discusses the effects of confining pressure and particle size on flow behavior. He notes that the flow of granular matter is often characterized by complex patterns, such as shear banding and segregation. The section acknowledges that predicting granular material behavior remains a formidable challenge. Section 10. Conclusion. Unity and challenges. Dijens concludes by reiterating the unifying themes that run through the book: the importance of mesoscopic interactions, the power of scaling concepts, and the applicability of phenomenological modeling. He emphasizes that soft matter comprises a diverse range of materials, unified by their sensitivity to thermal fluctuations and external forces. He acknowledges the limitations of the generalized approach, noting that specific details are often crucial for understanding the behavior of individual systems. He also points out the many challenges that remain in the field, such as the development of more accurate models for complex fluids and the understanding of non-equilibrium phenomena. Dijens reiterates his claim that soft matter research provides a fertile ground for interdisciplinary collaboration and offers the potential for technological innovation. The lasting contribution of soft matter resides not in its presentation of groundbreaking discoveries, but in its articulation of a coherent vision for the field, bridging disparate areas of research and inspiring a generation of scientists who explore the common threads that connect these fascinating materials. While some specific claims have been refined or superseded by later research, the overarching framework and the emphasis on scaling arguments continue to be valuable tools for understanding the complex behavior of soft matter.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.